Greetings from sunny Florida. Here I am at my third day at this National American Association of Physics teacher meeting. I've spent all day today, well, we started the first half today with Wii controllers and the physics of how they function and what you can do with them. Some really cool stuff I'll try to show you about them. And the second half of the day it's been biomedical physics. Again, more neat toys that I'll get to bring into class as this term and next term continues. Big thing I get when I come to these meetings is that there's simply physics everywhere, and all these new innovations that hit the market always come from physics class. That's where it all starts. So I'll share more of that with you later. Maybe at the end of this I'll show you some examples of what we've been doing. Meanwhile, let's get back to Newton's law of gravitation. Let's review what we did on Monday. Okay, so before we learn a little bit about tides here, let's again summarize what we've covered so far. The only new equation in this entire chapter is Newton's universal law of gravitation. Remember, this is an equation we can't derive. It's an equation we have to determine experimentally. One of the first things we did with Newton's law of gravitation is we used the definition of work to define a universal gravitational potential energy. And we came up with this. As you go through the chapter derives a dozen more equations on things like escape velocity and the specific radiuses of specific kinetic energies of spacecraft. Don't spend time trying to memorize those. As you're going through homework, always try to start from the one equation, F equals gmm over r squared. And often you're going to integrate that to find the universal gravitational potential energy, and those are the two things you're going to use to solve everything. So let's go on and try a conceptual question. Okay, those of us who've spent time on the coast know that there are approximately 2 high tides a day. These high tides are actually around 12 hours and 25 minutes apart. Explain this observation. Now, here's what I'd like you to do. I'd like you to spend, at least the next 7 to 10 minutes working with a neighbor to try to explain how, when you're sitting there on the beach in Newport, there are 2 tides a day. And I want you to start by drawing a picture. And once you develop a model to explain what causes these 2 high tides, I want you to, with your picture, draw a short couple sentences or a paragraph that explain why we see 2 tides a day. So explain what's going on to create these 2 tides. And I'd like you to hold on to this piece of paper and turn it in tomorrow when I'm back in town. I'm curious what you write. And of course, it's okay that your prediction's wrong. We don't care if your predictions are wrong. After you get together and discuss this in a group, we'll try to see what happens. So pause this now, and I'll come back in about 7 to 10 minutes. Thanks. Okay, thanks for taking a couple minutes to think about this. Again, in physics and everything in life, it's much better to spend time thinking about it and not just be given the answer. And because in your future jobs, that's what you're going to do. You're going to try to dream up new things that have never been thought before. So let's try this one. Okay, so we've got a problem. We're trying to figure out how these 2 high tides happen each day. First thing we're going to do is, of course, draw a picture. So what we have in this picture is we have an Earth. And probably sometime in your education you've learned that it is the moon that creates the tides. And there are 2 high tides a day. And we know that the Earth goes around its axis once every 24 hours. Now, this is a top view looking down on the Earth from above the North Pole. So the Earth is rotating around its axis once every 24 hours. And the moon, meanwhile, is going around, roughly every 27 days. So if this tide is happening roughly every 12 and a half hours, it can't be because the moon's whizzing around the Earth every 12 and a half hours. That would just make you dizzy if you were on the moon. Instead, it's got to be something else. So I think probably most of you explain that, well, there's got to be a high tide underneath the moon, because we know that the ocean is going to be gravitationally attracted towards the moon. Now, if there's 2 high tides a day, that must mean that the other high tide is on the other side of the planet. Okay, I've not drawn to the scale. I'm sorry. I'm still learning how to write when this computer is videotaping me at the same time. And how do we explain that bulge on the far side of the Earth? Well, we've drawn a picture. It still doesn't quite make sense to me. The next step is, of course, to try to draw a free body diagram. And in this case, we're going to draw 3 free body diagrams. First of all, we're going to draw a free body diagram on this ocean right here. And this ocean is closest to the moon, and by force equals GMM over R squared, we see that this ocean is closest to the moon. Therefore, every kilogram of ocean is going to be attracted towards the moon with a greater force than every kilogram of Earth, solid Earth that's inside the Earth, because the Earth is a little bit further away from the moon than that ocean is at this time. Therefore, if we draw a free body diagram for the Earth is going to have a free body diagram that's also attracted towards the moon, but the vector is not going to be quite as large. And then if we look at the far away ocean, it's also going to be attracted toward the moon, because gravity is an attractive force and only an attractive force, but it's the furthest away, so for every kilogram of ocean, you're going to have a much smaller net force or net acceleration than the other 2 components that we just talked about. So let's pretend we had 3 cars, each of equal mass. In this case it's mass per kilogram, but in this case each one with equal mass, and they're all accelerating with these acceleration vectors. So A1, A2, and A3. We know that A3 is going to accelerate faster than car 2, if these were cars, and therefore would be pulling away from car 2. Meanwhile, A1 is indeed accelerating towards the moon and accelerating in the same direction as the other 2 cars, if they're cars, and however, the other ones are accelerating faster, so poor car 1's being left behind. And that tide on the other side of the Earth, the one that we're going to experience 24 hours later, if we happen to be on this side of the Earth, 24 hours later, we have rotated around the Earth, and then we're in the middle of the next high tide. I hope that kind of makes sense. Let's try looking at a simulation here that might help just a little bit more. Okay, here's a slightly better drawing than the one I made by hand. Here you see the Earth, and you see the 2 high tides and the 2 low tides at 90 degrees with respect to the other. And we see the location of the moon. If we hit run, notice that the Earth is rotating underneath the moon once every 24 hours, while it takes 27 days for the moon to get all the way around the Earth. Notice that the 2 high tides follow the moon around the orbit as the moon orbits. And we can also try to throw the gravitational effect of the sun in. The sun exerts gravity on the Earth as well. And notice that when the sun gets put in, the gravity force adds to the gravity force of the moon. Basically it's vector addition. When the moon and the sun are at 90 degrees angle with respect to the Earth, notice that we have very small high and low tides. We call that a neap tide. Meanwhile, when the moon and the sun's gravity are adding vectorially together, we get what's called a spring tide. At a spring tide, you have super high tides and super low tides. You have the biggest range between them. The Earth's rotation impacts everything a little bit too. I'm going to click that, and let's turn off the sun for a second, and watch what happens to the oceans when you include the effects of the Earth's rotation. They jump ahead a little bit. And it turns out that jumping ahead a little bit is what's going to cause the moon to eventually escape the gravitational pull of the Earth. That's a different story. Let's get to that later. Okay, if you do want to learn more about tides and maybe things like phases of the moon and such, you might go down to the website below, astro.unl.edu/class-action, or just Google class action astronomy, and it'll bring you to this web page where they've just got tons of cool things. Remember, it was the study of the motion of the stars that eventually led us to this whole bit about gravity that Newton did a few hundred years ago, and it's all been a crazy ride since. If you click under lunar cycles and you wait while things are loading and go down to animations, you'll see that, okay, we saw the tidal bulge simulator. There's also fun things like the lunar phases simulator. I think that's a good one. Let's see. Yeah, it gives you good fun things to play with. Play around with those. It's a lot of fun. Okay, so let's go work on some sample problems. I'm going to stop this here because we're at the YouTube limit of 15 minutes, and go ahead and run the next clip after this.